Hello friend, my name is Raghavendra Agarwal. I am core network subject matter expert. Today we'll discuss on non-standalone network architecture versus standalone network architecture. Let's begin. So let's understand first the concept of non-standalone network architecture. Let's understand this with an example. Let's say that we have one service provider who is serving 2G, 3G and 4G customer, which means the network is already enabled with EPC core who is supporting 2G, 3G, 4G core network, and from the radio side the architecture is already enabled with eNode B or BTS, right, which is the radio network side of 2G, 3G and 4G, right. Now let's understand that the service provider is now allocated with 5G spectrum and want to launch the 5G service, right. So the fastest and the easiest way to launch the 5G service is the non-standalone architecture. The non-standalone architecture, the new component which will be added into the network is the 5G radio. There is no change in the core network. There is no change on the connectivity side of it, whether it is the backbone network MPLS, right. The only new component which will be added is the 5G radio, which we call as a new radio, 5G NR, right. Rest of the network will remain same. Maybe from the core side you have to slightly add some licenses, maybe some software upgrade to make that core network compatible with new radio. That may be slight change or just upgradation, software upgradation or the license addition, and you are done. Your complete network after enabling new radio as a radio side of 5G, your complete network is enabled for 5G service. You can onboard the 5G customer, right. So let's understand that the new radio is placed. Your EPC is now compatible to connect with new radio, and 5G user can start connecting to the network, right. So as soon as the 5G user will start connecting to the network and try to access the 5G service, in non-standalone architecture all signaling packet, whether it is attach or PDU, all the signaling piece of it will be forwarded from new radio to underlying LT radio, which is eNode B, and then eNode B will forward all the signaling packet to the MME, which is the entry point of EPC core, by using the existing interface. So the existing interface, which we call as S1AP, right, NAS signaling, will be used to forward the signaling packet being originated by 5G user who is trying accessing 5G service. So the 5G user is connected to new radio. New radio will further forward the signaling packet to the underlying LT radio, which is the 4G radio, and then 4G radio will forward the complete signaling packet to the MME via using the existing interface, right. So only the new radio get added, remaining the signaling interface between the MME and eNode B will be used for 5G user as well, right. There is no change at all. So here the new radio will work as a secondary RAT, and the eNode B, underlying eNode B, will be used as a master RAT. Now let's understand the payload piece of it, which is the user plane. For user plane, there will be a direct connection from S gateway to new radio. There will be S1U connectivity between the S gateway to the new radio for actual payload traffic. So the signaling will be via the underlying E node B, but the payload will be via direct connectivity between the S gateway to the new radio towards the user. So this kind of setup is called the non-standalone architecture. The only addition is the new radio from the radio side. Rest complete network is same. There is no change. Right? Let's understand now the concept of standalone architecture. The standalone architecture, the major change is from the core side. So earlier in non-standalone, we were able to use the EPC core, which is the 4G core originally, right? But in standalone, there is a complete shift in the core side. The core side is based on service-based architecture, which is enabled by cloud native technology or microservice-based architecture. So the complete shift will happen from the core side in case of a standalone architecture. So your EPC core will further evolve to the 5G core. So we'll have different new elements from the core side. Let's say AMF, SMF, right? And all these network function will be connected via service-based interfaces as SBI, right? And forming the 5GC, which we call as the 5G core, right? So once the operator is having the 5G core ready, then the operator can move toward the standalone architecture. So in a standalone architecture, the user will connect to the new radio, which is already there, and this time the new radio will forward the control piece of the control plane signaling, which was earlier forwarded to E node B. Now the new radio can forward that signaling packet directly to 5G core. Right? So the new radio will have the interface with 5G core directly. So the 5G user who is trying accessing the 5G network or 5G service will be served by 5G core. Now this time there is no role of EPC. The complete 5G signaling plus 5G payload will be served via the 5G core. The complete traffic will be routed from handset from the user device to new radio, and new radio will forward the complete signaling towards the 5G core. The major shift in the 5G core is the core side of it. You have to make that core ready, then only you can launch the standalone architecture. Right? Let's understand more the differences between the NSA and SA architecture, maybe in the subsequent slide. From the architecture point of view, let's again touch base the core architecture. From the core architecture point of view, the non-standalone architecture, as we discussed, will use the existing EPC core. The existing EPC core, which is serving 2G, 3G and 4G customer, by making few software changes or license changes, that core will be enabled to serve the 5G customer also in non-standalone architecture. But in standalone architecture, there is a drastic shift of the architecture, core network architecture itself. There will be new network function will get added. There will be change into the connectivity of all the network functions. Okay, that is a service-based architecture. So once your 5GC, which is 5G core, is ready, then only you can launch the 5G service. So there is a drastic change to the core network architecture in standalone. Let's understand the NR connectivity, the new radio connectivity. In case of non-standalone architecture, the new radio will forward the signaling packet to the underlying LTE radio, and then LTE radio will forward the signaling packet to the existing MME, which is the entry point of the core. But in case of standalone, the new radio will directly integrate it with 5G core, which is AMF, SMF, right? AMF is the entry point, so where the signaling will be forwarded by the new radio, right? So there is a change in the connectivity in NR in case of NSA versus SA. Let's understand the service. So for example, if there is no change into the core network and operator launch the 5G services via using the non-standalone architecture mode, then the service which can be offered is the high-speed connectivity, because your radio network is now 5G enabled, your spectrum is 5G enabled, so you can get the higher speed, your bandwidth will be high and you can get better speed, right? But apart from that, there is other use cases of 5G which is related to URLLC, which is ultra reliable low latency communication, AR/VR, right? Smart industry, right? Maybe connected car, right? Maybe the smart industry, or let's say that factories you are trying to, means in 5G we are trying to automate the factory, right? AR/VR kind of use cases, right? So that use cases will not be possible in a non-standalone architecture because it doesn't support low latency, it doesn't support we can say the network slicing, right? So that will be limitation in terms of services being offered in non-standalone architecture vis-a-vis the standalone architecture. Time to market. As we discussed that in non-standalone architecture, the network function which get added into the network is the G node or the new radio. Once the new radio is there, which is 5G radio, you can immediately launch the 5G service. You don't need to change into the core network. So that is why it is faster deployment. Your radio is done, your radio is integrated with core, you can immediately launch the service. This is the fastest way to deploy the 5G service. But in case of a standalone, as there is a shift in the core network architecture, so you have to make your 5G core ready and you have to test each and every function, right? And that is the time consuming process. Once all these functions get tested, then only you can launch the 5G service. It is time consuming. Network slicing. In non-standalone architecture, as we are using the existing EPC, so the network slicing will not be supported. You can maybe use the existing network, you can differentiate based on APN, based on dedicated core, or based on usage type, that you can do, but that is a very limited flexibility in terms of slicing. It's not end-to-end slicing, it's just you can differentiate, or maybe you can treat requirement of different APN differently in core, but the slicing will not be there. There is no end-to-end slicing from core to radio to transport. There is no slicing at all, right? You can just play with QCI, QS, ARP, and there is a limited way you can play. But in case of standalone architecture, there is a separate slice you can create end to end from core to transport to radio, and you can allocate the resources so that you can maybe give a dedicated bandwidth or different treatment for different use cases. If it is low latency, you can give the network different network slice. If it is high bandwidth requirement, you can design the network differently and you can create a different network slice, right? Or maybe it is massive connection, you don't need much bandwidth, right? And in that case also you can design the network differently and you can create a separate slice for that use case. So that flexibility is there in standalone architecture. Cloud approach. In case of non-standalone, as our EPC is virtualized, but in case of 5G core, whenever we go and place or maybe build the 5G core into the network, the 5G core component is the cloud native and a microservice based architecture. So you have to make that platform ready. You have to make that operationally you have to make sure that your tooling in place to monitor the microservice architecture, right? So complete shift into the platform architecture also, and the network function will also get evolved in case of 5G core. There is a drastic change into the network architecture. Capex. In case of non-standalone, there is a low capex because your 5G core is not required. You can just change few licenses and maybe some release version and you are done. You just add the new radio as a connectivity, as a radio part piece of it. You don't need to change much on the transport side. You don't need to change much on the core side, and the network is ready for 5G service. But in case of a standalone, as you have to place new 5G core, so you have to make that cloud network ready, the cloud native support ready. You have to make the new network function get deployed into the network, right? 5G core need to be deployed. So it's a high capex requirement. So there is a upfront cost. Once that capex is deployed, your network is ready, then only you can launch the 5G service. So these are the major differences we understand between NSA and SA, right? So that's it for today on this topic. We'll reconnect again, right? We'll reconnect again maybe with some new topic. Thank you so much.